Load. We're good to go. All right.
Yes.
Well, thank you so much for that introduction, Michelle, and thanks to all of you for being here today and for giving me this platform to talk with you about some of the research we've been doing. And what I'll be talking about today, I'll be presenting it, but it really does represent the work of so many people that have been contributing ideas and time and effort into bringing all of these different components together to tell this story about how green stormwater infrastructure changes and works through time. So in this presentation, as you saw through the title, we'll be talking about coupling infiltration and morphology models to understand the dynamics of green stormwater infrastructure, but also to relate that back to how rivers and floodplains are working too at the end. So as Michelle mentioned, just because of the platform, since we're meeting online, it would be easier for me to answer all of the questions at the end. But even if a question pops into your head a week from now, I would love it if you reached out to me and wanted to discuss things further, because I'm happy to talk about this research with anybody, even people on the street walking by too slow. I might just stop. But I'll jump in today and talk a little bit about why I'm so passionate about this and why I think it matters a lot. A lot of our population lives in urban areas, and we can see how much this is growing in North America. Here we have some examples of just how quickly our urban landscapes are growing, and it's a worldwide trend. There's so many opportunities that are happening in the urban landscape, opportunities, business, and education that's really drawing a lot of people in, not just in North America, but across the world. And as so many people are coming into the urban landscape, it's changing the face of this landscape, and it's resulting in a lot of changes to our stormwater systems, the demand on our stormwater systems, and people that are vulnerable to flooding, not just the extreme events that we think, and of course those matter a lot, but also the nuisance flooding, that flooding that might happen a couple times a year. And what we've been seeing through studies is that this is becoming more and more common, more and more frequent through time, and putting a heavier tax on our stormwater systems. The repercussions of that are often affecting the most vulnerable populations. And so finding ways to get around that and to mitigate what's happening with our stormwater systems, what's happening then in turn to the water quality in our stream, is a really important topic and something that's going to be growing in importance through time. One solution that's becoming increasingly prevalent to meeting stormwater demands is green stormwater infrastructure. So this is an ecological system that's using nature-based solutions to harness stormwater, and it's attenuating the flood pulse, but it's also having impacts on the water quality and additional secondary impacts that have been really expansive. So here we have an example of green stormwater infrastructure where you have some inflow coming in, energy dissipation, and then water is going into some vegetated area typically. And these can look a lot of different ways. This is just one example that we have here. And in this example, uses bioinfiltration to process the stormwater. And that's the example that we'll be using for a lot of a case study that I'll be talking about today. So why does this matter? Well, this is from an old paper in 1967 showing how land cover change over time is related to what your hydrograph looks like. And this was published by Woolman in 1967, and what he suggested is that you started off with this, sorry, not the hydrograph, but the sediment yield. You started off with this lower sediment yield when it's forested, and then you start developing the land through agriculture and through different types of land and watershed development. And then once you get to urban, you have this constructed area, and you get a whole lot of sediment coming into the system. And then after construction, somewhere in this area, once everything's urbanized, your sediment load is going way down. But you can see it's a dashed line. We don't really know what the sediment in an urban area looks like. There's no real description, and it depends a lot on where you are. Does the sediment in Seattle look the same way it does in Philadelphia? No, there's a lot of drivers that are forcing that to look a lot different in different places. But it's a really important thing to consider in the sustainability of our infrastructure. So here we have an example of GSI at Villanova's campus. And if you're ever in Philadelphia, I'd love to show you around our campus. We've turned it into a hydrology lab, and we have a lot of GSI that we've implemented really fine monitoring equipment. This is called the bioinfiltration basin. This has been monitored for 20 years, and we've created a really nice database of all of this monitoring data. And what we've learned from this we've worked with Philadelphia's water department a lot to help them develop their green stormwater infrastructure program across the city, which now has 6,000 different installations. And they're certainly not alone. Similar cases exist in New York City and in Portland, Detroit, and around the world. We're seeing more and more of this. It's becoming increasingly prevalent. And in Seattle too, there's a huge program, as I'm sure many of you know far better than I do. Here we just have some examples from the Rainwise project and also the Swale on Yale, which I really enjoyed looking at. It looks like a really interesting program. So I had fun reading about it over the past week. But as we learn more about these systems, we're finding that there's some real challenges, and a lot of those challenges are around sediment and around maintenance. And if you're like me, every time it rains, I like to go out and look in the gutters and think about where the sediment's moving and where it's building up. And these pictures I just took around Philadelphia, but I'm sure you have similar images in Seattle and all around the world that you can see with the sediment collecting and causing blockages, and it's affecting the way some of our infrastructure functions. And Del Grosso et al. Published a paper in 2018, this is one of their images from that paper, looking at what causes maintenance issues within green stormwater infrastructure. And if you look at this, several of these are related to what's moving into the GSI or what's moving into the inlet area of these GSI and causing problems in the function over time. So erosion and sedimentation and blockages, debris, these are all key issues. And what we've learned from the programs in Philadelphia and also from programs in DC and around the country, I'm sure in Seattle too, you've seen this, that maintenance for GSI can be a real challenge. It's incredibly expensive. It's something that's hard to do through big machines. You don't want to force compaction in these infrastructure that are relying on infiltration. And so it takes a lot of time, a lot of effort to maintain these systems. So what if we could maybe design these in a different way so that we could think about maintenance less through a data-driven maintenance and move to different types of designs? So I've listed here several papers that are leading to this, calling for this type of action that we've published over the past few years, and even some that are about to come out. I'm happy to share these with you if you like. But here we wanted to take this idea and put it together and develop a framework for modeling green stormwater infrastructure surface dynamics based on an understanding of what's happening with the shear stress and the sediment flux. And if we could model this for a GSI system, or think about this as an approach for thinking about GSI design, could we design our GSI then to, instead of maintaining the entire 100% of the GSI surface, maybe just maintaining 20 or 10 or 5? If you were to force deposition in one area, would that reduce the amount of maintenance that you need? And even if you had an idea for how quickly these were filling up with fine sediments or going to run into maintenance problems, then maybe you could schedule your maintenance in a data-driven way, that would allow you to invest less in your maintenance through time. So what happens to sediment when it comes in? Well, we've started looking at this a while ago, and I was coming from a background where I thought a lot about rivers. And to me, it immediately started to kind of look like a river channel. You can see the way it starts to meander through the flow path, and as it moves through the system, it's bringing sediments through the system with it. So water's coming off the highway deck or the roadway, and you have a certain amount of sediment that's coming off of that area. Maybe you have a sediment pretreatment that's capturing some of the sediment, but not all of it, and often not the fines that are making their way through the system anyways. And then it's going into the system and being deposited along the way at different points. And you can see different depositional features the same way that you might see in a small stream. The location for this study is part of an I-95 rehabilitation project shown at the top in different colors. And then at the bottom in this red circle, this is where we're actually modeling. I'll refer to it as SMPA. So there's several SMP stormwater management practices along this corridor, and we're going to focus in at SMPA. And here we just have an image where it's divided into three sections, an upstream section, and then a gabion area, and then a downstream section. And we're going to focus on the downstream section because this is the area that was getting a whole lot of sediment deposit. So as they rehabilitate all of I-95, all of the water coming off of that is being processed by green stormwater infrastructure. And all this is going to come out to be around 80 to 90 different green stormwater infrastructure installations. And Villanova's role in this is to look at the efficiency and how to make this many SMPs work as efficiently as possible. So the approach in modeling this to think about where the sediment's going is first to evaluate the spatial and temporal dynamics of the GSI through soils and sediments. So we did this through a three-pronged approach: field testing, laboratory analysis, and modeling. By providing this insight, we hope to minimize excessive erosion, minimize the risk of clogging, and then help to create a more targeted maintenance and also design practices to maintain the longevity and the sustainable function of these systems. So essentially what we're doing is we're integrating an approach of water resources and fluvial morphology and geotechnical analysis to come together for a solution of understanding where sediments are going on the surface. And a lot of this work that I'm presenting was done by Richard Ampelma, Dr. Richard Ampelma, who was the PhD student on this project. So field testing was done 2 to 3 times a year. Core samples were taken. In addition to that, infiltration was done. And you can see all of these white dots along here where infiltration tests were done and core samples were taken at 6-inch cores. So we have our Saturo infiltrometer up at the top, and then also an example of the cores that were being taken. In addition to that field testing, we also used a dirt bag, which is the official name of this apparatus. It's not just a field apparatus that I'm frustrated with, but it's a giant pervious bag that captures the stormwater coming in and then would leach out the stormwater, and we would have the sediments remaining. You can see the sediments in the bowl at the bottom, where we would then measure those sediments that had come in through the stormwater. We also did topographic and LiDAR surveys of the SMP, and then took the data that we collected and took it back to the lab for characterization of the particle size distribution of the sediments that were collected and the soil that was collected through the soil cores. We analyzed the plasticity, the organic content, classified the soils, looked at the density, the hydraulic conductivity, and the soil water characteristics curves. And this was all overseen by my colleague, Dr. Kristen Sample-Lord. This is just an example of our soil cores that we had. And as I mentioned, we went out a few times a year and collected this data. And as you can see, from the fall of 2017 to the fall of 2019, and now we've even gone beyond that, there's not a huge change that happened. So that's a good thing. The soil's staying the same. It should be functioning the same, and it was functioning the same. We saw that the infiltration test, the field hydraulic conductivity was fairly constant throughout this time. So we weren't having a whole lot of changes. The SMPA was performing the same consistently through time, which is great. But what was happening to all the sediments that were coming in? We could see them coming in, we could see that channel forming, and we knew that things weren't staying constant. It's not a closed system. You had different soils coming in through the sediment. The soils were being affected by the sediments coming in, but they weren't responding to it. And so we were interested as to why, because we know that this can be an issue in the performance of some SMPs. So we started modeling this too, and we thought about how to best model it. We're interested in what's happening at the surface. And so we manipulated a river model that already existed. So our geomorphic modeling procedure to look at how sediments move through the system started with the use of a DEM, a digital elevation model. We then created a hydraulic simulation for what was happening on the surface with the surface water. This included an infiltration simulation. We included the Navier-Stokes. This was part of EWRI software, the International River Cooperation software. That then went to a morphology simulation using the Yallen equations. We updated the DEM and then went to the next storm event and repeated the process again. And so we built storm event on storm event on storm event so that we could look at how the surface was changing through time. And like I said, more information about this can be found in the dissertation of Dr. Ampelma, but also this is being published right now and the results will hopefully be out soon. So the data assimilation, we used a whole lot of data, the LiDAR, hydrographs that were being collected on site, ponding depth, and also the saturated hydraulic conductivity from our test in the field. And we put this all together. And to account for infiltration, the big challenge in applying EWRI and the simulation of what was happening at the surface is, unlike rivers, you have a whole lot of infiltration that's really a big part of the water balance within the GSI itself. And so this wasn't being accounted for the same way in the river models that we attempted to use. So we had to take a side step out to account for that. And there were cases, here's an event where we were able to, I'll just show you an example here from event 2, where we basically just took off part of the hydrograph to account for that infiltration. So you can see the inflow in the solid line and then the dashed volumetric infiltration rate that was calculated through a MATLAB program. And we applied this to the hydraulics simulation, and we could use observed ponding depths to compare to our predicted accuracy. And in certain storm events, this wasn't great, but overall, we ended up with a pretty good performance of the model, and we're able to model 33 events quite accurately. So we applied this and we were able to get results where we could see the shear stress distribution in the surface of the GSI itself. And so you could see areas where you had higher shear stress and a greater predicted change, and therefore correlating to where we would expect there to be more sediment flux and where you might have less sediment flux or more deposition. But still, we knew that even though we had this soil flux happening, things weren't really changing in the GSI itself. And so while I was thinking about this in terms of rivers, my colleague, Dr. Kristen Sampelord, she's a geotechnical engineer, started thinking about this in terms of mine tailings dams. And so we ended up applying a criteria for mine tailings dams to think about how the media of the GSI might instead be working as a filter. So here we just have a cartoon showing why we think that maybe the deposition of sediments is or isn't affecting the infiltration rates of the engineered media. So at a certain grain size, your engineered media can actually work as a filter to what your deposited sediments are. And so we applied this criteria to our media for the soil of the SMP. So the solid line here shows the measured SMP soil media for SMP-A. And then we have, based on the criteria for mine tailings dams, the envelope of compatible soil for that same SMP. And then we have a line here showing the D50 of highway sediments according to a paper by Selbig and Bannerman. And of course, these highway sediments are going to vary, but you can see, depending on what your D50 is and what the distribution of that D50 is, you're likely within a compatible range for that soil. Knowing the D50 doesn't give you the whole PSD, obviously, right? But what that tells us is how at risk you might be in terms of clogging your media for your soil. So we thought about this, and we thought about, well, what does an urban sediment look like? And are there certain areas where you might be more at risk of clogging than other areas? Because we know that often clogging will happen in the first few years of a sediment or of a GSI life. You also know that things like construction dust can be detrimental to the performance, to the infiltration performance of a GSI. So then we started collecting data and going through and thinking about what D50s look like and where you might be more at risk or less at risk of clogging your soil media. So we mined the literature, and we came up with a distribution based on 70 different studies of what D50 looks like for runoff of different types. And what we found was roads with more usage generally had a higher D50 than roads with less usage. There was also a wider range in those roads compared to things like parking lots or mixed use surfaces. And then we started comparing this just to our example from our one GSI of SMPA. And we found that if you're thinking about sediments that might be coming from a parking lot, your SMP is potentially more at risk from clogging due to fine sediments than it would be from that of a highway. And then in addition to that, we started thinking about, well, what does that mean? That's talking about what's moving into the soil, right? That these fines are being filtered by the media. But what does that mean on the environmental side? If we're thinking about nutrients, phosphates, metals being collected by GSI and then moving into the media. So this is another example. This is an example from a GSI that's on Villanova's campus. I showed it earlier. It's the BTI, the bioinfiltration basin that we have. This is 20 years old. And for the past 20 years, it's been working great. And so we started looking at the soil samples here, Dr. Sample Lord and I, and we also modeled this with ArcHydro to see where you might have more flow accumulation and less flow accumulation. And what we saw was that the areas that are being inundated frequently and have a higher shear stress running off of it had lower rates of nitrogen. But areas where you had more ponding, areas like 4 and 5 that are in the basin here, there your nitrogen percentages were higher. And so you can see 4 and 5 are quite a bit higher. 3 and 1 got less water altogether. And so the nitrogen rates are a bit lower there. Point 2 is an interesting case where the water's just running over it pretty quickly. And so you have some water, but it's not ponding the same as it is at 4 and 5. And so your nitrogen that you're finding at those samples is lower. Well, this is great because it helps us understand where different things are building up in GSI. And then we can think about the maintenance around these systems a little bit more and think about it as opposed to a one-size-fits-all matter. Maybe we can alter the geometry of these to think about them more efficiently. But we can also then apply this idea to how we're thinking about rivers. This is an example from Darby Creek, which is in the Philadelphia area also. And we took this idea of the shear stress and what's being deposited and thought about PAHs as opposed to thinking about nitrogen. So PAHs, polyaromatic hydrocarbons, are a carcinogen, and they are coming from a Superfund site that's just upstream of this study area here in Philadelphia. So what we did is we modeled the shear stress across this area, and then we went out and we took soil samples and tested them for PAHs. And what we found was that in the bed, where you had a lot of constant shear stress, the PAHs were a lot lower than they were in the banks. And then we looked out to the floodplain and found that the PAHs were even lower in the floodplain in those areas that were getting really infrequent inundation. So the banks that aren't underwater all the time, but they're getting more frequent inundation than the deeper floodplain, have the highest rates of PAHs. This was recently published in Frontiers. So in conclusion, the infiltration rates in the soil mixture in the SMPA have remained pretty stable over time, even though you have sediments coming in. But the reason they've been able to remain stable is because that media is acting as a filter for the fine sediments that are coming in. Because of the particle size distribution of the sediments that are coming in, it's able to perform that way. So the restriction of fine sediments to the near surface is consistent with the traditional granular filter concepts. Testing is currently underway to evaluate the limits of that sediment soil capability. So we're running a whole bunch of different tests to see exactly where we can clog the soil. So if you're designing a GSI that's draining a parking lot, should it look the same as the GSI that you're designing for a highway? What should your media specs look like? And then for the GSI morphology, we can leverage this to enhance the design and to help assess the potential for GSI to be susceptible to erosion and deposition, and maybe alter the way that it's laid out to maximize or minimize our maintenance over time. And further, this information we can then use and transfer that knowledge to understand how rivers and floodplains change through time. So here's a few of the manuscripts that I mentioned. Most of these are already out, but a few will be coming out in the next few weeks. I'm happy to share any of these with you if you like. Just send me an email. And I'd like to thank all of the funders of this research, the Pennsylvania Department of Transportation, AECOM, and the Department of Environmental Protection here in Pennsylvania, as well as everyone that contributed to this, Dr. Kristen Samplelord, Dr. Rob Traver, Dr. Bridget Wadzik, Dr. Amanda Hest, Dr. Zaremba, Dr. Ampuma, Dr. Husseini, and then all of the graduate students too listed here. So they're really fabulous people contributing to this. And with that, I'd just like to thank you and open it up for any questions.
Thank you very much. Very informative. Very intriguing. I already have hand clapping and everything. All right. So as we mentioned before, please feel free to write your questions in the chat box, or if you want to turn on your mic and ask your question, do that now. It does look like there is a question in the chat. It says, it's from Scott, and it says, did you consider the potential for root penetration and bioturbation to maintain infiltration rates?
Yeah, thanks, Scott. That's a great question. And I think one of the great challenges of working in GSI is that these are such dynamic systems and there's so much happening in them. It's really difficult to do a controlled study. I think one reason why the BTI is functioning, it's actually increasing in its performance over time. And there's two big things I would say there. One is the root growth, and the more established plants are able to perform better, and they're helping the performance of the GSI through time. But also, we've been studying this so closely for 20 years. We're not the first ones to go out and take soil samples. We've essentially, through research, we're doing a really great job aerating the BTI all the time. And that's probably contributing, it's got to be affecting what's happening at the surface there too. And when we started studying SMPA, the SMP that I talked about for most of the time, when we initially started there, it was new. It was a blank slate, which made it a great place to study. But those plants started to grow over time and definitely did change the surface and change the function of the GSI too.
Looks like the next question is from Homero, and it says, how do you measure inflow to GSI and water levels in the GSI?
Okay, that's a great question too. So the inflow to GSI, we measure through what we call a blue siren, and we'll put a weir in and then put the blue siren behind that, and it measures it measures the flow for us. And then we use pressure transducers to measure depth. We have, as I mentioned, 20 years spanning 15 sites of both discrete and continuous data. So we have about 5-minute data for 20 years at one site and several other sites. So recently I took all of this data and restructured it into an observation data model based on Quasi's format. And because the hardest thing actually about the 5-minute data is being able to serve it in a way that you can extract the data and analyze it. That's the really tough thing. So we rewrote Quasi's data model for specifically to stormwater. And hopefully we'll be putting that paper out soon, which talks a little bit more about how we're getting this data and how we're using it. But I think getting all of the data and getting it to to all the people that could possibly need it is a real challenge in stormwater. You have a lot of data silos for good reasons, but it's a challenge in holistic analysis.
Great. Next question says, what was the significance for sorry, let me read that again. What was the significance for sampling for nitrogen and PAH?
Okay, so when we were looking at nitrogen, and one study funded by the Department of Environmental Protection was looking at where nitrogens, fines, and phosphates end up in a GSI. And so we know that GSI are capturing these. They're quite good at improving the water quality, but where are they really good at it? So if we understood where you're capturing the most nitrogen, could we then help improve the performance of the GSI and improving water quality over time? So that was the focus of that portion. And also understanding where the fines were going, of course, was related to the infiltration function. Through another parallel study, we've also been looking at a wetland and where the nitrates and where the nitrogen is falling out of the system and where we see the greatest improvements spatially. And by understanding the spatial changes, we can then start to analyze that relative to the different types of plants that are there and the residence times of the water, and just understand how the whole system's working together. The PAHs was part of another study that was understanding just where these contaminants that are carcinogenic contaminants are being deposited in the environment. And I talked about Darby Creek. This is a portion of Philadelphia that's affected. It's immediately downstream of a Superfund site. It's an environmental justice issue that's happening in Philadelphia. And it's a big problem because we know that the PAHs will make people sick, but we don't know exactly where they're ending up in the environment. So if we can understand where they're depositing and then how they're making their way into the soil, then that will help us understand better how to amend the problem.
All right, looks like this is the last question so far, but feel free to keep typing in and asking questions. It says, what is the limiting factor for a GSI's lifetime? Contamination, silting up, etc.
It really depends on the GSI and the environment that it's draining. The most common reported problems from the publications appear to be around sedimentation, debris, clogging, and erosion. I don't know that anybody can definitively say that because a lot of the data doesn't exist. For good reason, a lot of municipalities don't choose to make their data public when something isn't working well, right? You can see why that would be a bit of a lightning rod for some places. But based on the few publications that have come out about it, it seems like a lot of the issues tend to be around those. And maybe the biggest driver behind that's responding that isn't a flaw in the design, but just that the urban environment is so dynamic that things are constantly changing. If you have construction right next to a GSI and a bunch of fine construction dust comes and clogs that, you can see how that would be a major issue. And I'm also speaking from the perspective of being on the East Coast and watching a lot of these systems, talking frequently with colleagues in New York and New Jersey and Washington and Virginia, whereas I imagine the problems that are in different places with different climates, like say Denver, might be subjected to other types of challenges, like keeping your plants alive through droughts and things of that nature. The West Coast, last summer, you had this really big heat event, right? I'd be curious to know how that affected things. So I'm only speaking from one perspective. That's what's affecting us here, but I can imagine, given different climates or lithologies that you're subjected to, you might have different challenges to overcome.
Interesting. The next question says, have you done any work tracking sediment in combined sewer systems? Do you have any pointers to this type of work? We have a lot of sediment here in Seattle in our combined sewer system.
Oh, I'm so interested in this, and I would love to get that data, but it's hard to come by. And getting the full sediment load, both what's moving along the bed, that coarser portion, and the suspended portion, is really challenging to do. And it's the full portion of the sediment load that's going to tell you if something's clogging or not, right? So I reported the D50 because that's what we can get, but it's the entire particle size distribution curve that actually is going to control whether or not something's clogging. So what I've started to do is, and I'm happy to send any of these out to any of you, I've been sending out 2-inch core samples to friends and colleagues around the US. And what I say is, if you're walking along an urban stream and you have a floodplain area, if you could just put it in, take it out, put the coordinates on it, take a picture, and send me the sample, and I'm processing it. So I'm just getting the top 2 inches of what's happening in those urban floodplains to try to understand what urban sediments look like more. So specific to CSOs, it probably relies a lot on the system and how well the system is sized relative to what's happened in the watershed too. Because as our systems in Philadelphia are really old CSO systems, now as the city's changed so much, it's altering the amount of sediment and flow that's going into these systems and how frequently you have your overflows. That's a great question. I'd love to know more about the sediment in CSOs.
Looks like that's the last questions in the chat. I don't know if anyone has anyone other that they want to either type out or they're brave enough to turn on their mics. Give people takers.
I know, yeah, for me too, I'll be thinking about something and a week later a question might pop into my mind. It takes me a little while sometimes, so please do feel free to reach out to me, and I'm always happy to talk about urban sediments.
Great. Well, thank you very much. I mean, I'll do one last kind of plug before give people a few more minutes to think of their questions. But thank you very much, Virginia. It was very informative, and we're very happy to have you here. And I think everyone here, I'm going to speak on behalf of everyone, that we enjoyed your presentation. Just a reminder to everyone else, well, Virginia, you're more than welcome to join. But next month, our meeting is on March 17th. We're going to have Emily McCain from Washington Department of Fish and Wildlife speaking. So as usual, our 12 to 1 topic, or 12 to 1 time. But yeah, I guess last call for any questions. Otherwise, we'll give you back a few more.
I have a quick question. So there's been a lot of talks here about the fact that the bioretention soil actually over time helps the bioretention cells work better. And you're saying that you're getting the same flow rates. Have you done any testing on anything where you didn't have any sediments going into them?
We've started doing some testing with pre-treatments. Is that what you mean, or like a controlled lab test where we just have flow going into the soil?
Maybe a controlled Because what they're saying is that over time, the bioretentions actually, when they dug down into the soils, the media filter was going down farther into the existing soils and making it drain better, is what the claims are. And I like that.
Yeah, so we have not done a controlled study like that. We currently have a proposal in for tubs of soil that we are doing, that we would then do different controlled studies on. A lot of this was more focused on salts and thinking about how salts change the structure of the soil through time. But I'm sure we would have one that was just controlled, like you mentioned. So we've talked a bit about, really understanding what it means if you have people frequently walking through a GSI, like our GSI on campus. Students just walk through them, and that's fine. How much it affects it, we don't really know. And so there's like lots of little things that we'd like to try to pull out, and hopefully we'll be doing more controlled studies soon. But these open living systems are really challenging to tease out individual factors.
Thank you.
Sure, thank you.
All right, last call. Anyone else? All right. Well, with that, I think I'm going to close out the meeting then. Thank you again, Virginia. And like she mentioned, feel free to reach out to her. And thank you all for joining us today.
Thanks, everyone.
Thank you.